Good afternoon, everyone, and welcome back to the JLab Users Organization annual meeting. I'm Carlos Muñoz, and I'll be sharing the last session today. So we have 4 talks in this session. Kindly ask all speakers to keep their presentations to the allocated time, which is 20 minutes, so that we can have 5-minute discussion after each talk. We should also try to keep the time so that we don't delay the EAC simulation Q&A session, that it's scheduled right after the meeting. So the first talk of the session is by Matt Stolt from Slack, who will be telling us about the heavy photon search experiment. So Matt, please go ahead.
All right, thanks for having me. My name is Matt, and I'm going to tell you all about heavy photons. All right, so a heavy photon, which is also referred to as a dark photon or an A prime, it's a hypothetical vector boson that couples indirectly to electromagnetic particles. In HPS, we're an experiment at JLab in Hall B, a fixed target experiment, and we're dedicated to searching for this particle. And we do so through 2 distinct methods. The first is a resonance search, and the second is a displaced vertex search. So in this talk, I'll introduce heavy photons and their motivations, as well as an experimental overview. What I'll focus on is the 2016 engineering run, and today we're showing our first public results for both of these searches, so that's very exciting. And then lastly, I'll talk briefly about our most recent run. So what are heavy photons? So they arise from an additional abelian gauge symmetry, U1 prime, which causes a kinetic mixing term here, in which the standard model photon mixes with an A prime. And what this does is that it induces a weak effective coupling to standard model fermions, suppressed by a factor of epsilon that we call the kinetic mixing parameter, or just a coupling constant for short. And one of the prime motivations, if you look here on the right, is a concept called light dark matter, which is dark matter on the MeV to GeV scale. This requires a new comparably light force carrier, such as an A prime. And it does so because of a cosmological bound called the Lee-Weinberg bound, which requires dark matter mass to be above 2 GeV if it interacts with standard model particles. So A primes are a new light force carrier that can be used to circumvent this bound. And for instance, it's shown in this diagram up here. Through kinetic mixing, dark matter and standard model matter can interact with each other indirectly. So this is a 2-parameter model, epsilon and mass. And if we look at a theoretically favored region of parameter space, we can ask what types of experiments can probe this region. And the first type for large coupling up here, these are typically bump hunts, where you search for a resonance peak at the A prime mass. For example, we have Apex here, which is a JLab experiment in Hall A. Now there's an inverse relationship between the coupling and the lifetime, such that as you go down in this plot, secondary vertices are resolvable. And particularly here in the lower left-hand region, you can probe this region by beam dump experiments, such as SLACI 137, where a high-intensity electron beam is incident on a target, and this hill here would filter out all the standard model particles, but A primes would not interact. They would live for a long time, for hundreds of meters, and then decay in this volume here. So beam dumps can probe this region down here. Now there's this region in the middle that's quite difficult to probe because of small cross sections and short lifetimes. And this sort of edge here is limited by the size of the beam dump. So in order to probe from this direction, one can imagine sort of shrinking this beam dump as much as possible. However, the issue you get to when doing that is that you can no longer filter out all your standard model particles. And because of this, if you shrink it enough, you need to actually be able to reconstruct the decay vertex of an A prime. And that's sort of the principle of HPS. We want to reconstruct A prime so we can probe this region here. And to do that, we have our apparatus, which consists of three main components. The first is a silicon vertex tracker, or SVT. It's right here in the middle of our detector. This reconstructs mass and vertex positions. Behind that, we have our electromagnetic calorimeter, which we use for triggering on E plus E minus pairs. And then lastly, we have a dipole magnet, which spreads the E plus E minus pairs and provides a curvature for a momentum measurement. And you can see this process on this cartoon on the right. So before I get into more details on the SVT, it's important to understand some heavy photon kinematics. So in this experiment, A primes are produced through a process analogous to Bremsstrahlung called dark Bremsstrahlung, where an electron beam is incident on a metal foil, which brems off an A prime, and that decays into E plus T minus pairs. Now, in this scenario, A primes take most of the beam energy, and these E plus E minus decay products are forward with a very small opening angle. And because of this, our detector has to be very close to the beam plane, because our acceptance has to be very forward. And so this is sort of one of the design considerations of the SVT. You can see here it's inside a vacuum chamber, and it consists of 6 layers of silicon microstrips. Each layer consists of 2 sensors. One is parallel to the beam plane, one is tilted at a slight stereo angle that allows for a 3D hit reconstruction. Now this SVT is split into 2 halves, top and bottom, such that most of the beam electrons can go through the detector. Now, as I said, we want as much acceptance as possible. So in our case, we get down to plus or minus 15 milliradians. And we also want layer 1 of the SVT to be as close to the target as possible for optimal vertex resolution. If you do the geometry, that works out to the fact that our first layer is about half a millimeter from the beam axis, which is far closer than any other experiment that I've heard of. And because of this, layers 1 through 3 are retractable from the beam, so that we can tune the beam without damaging our detector. And layers 4 through 6 are double wide for acceptances purposes. And on the right is a picture of the SVT during construction, along with a former graduate student. One of these is the top and one is the bottom. Basically, they go on top of each other like that. So far we have 3 data runs. 2 of them were engineering runs. And the one I'm going to focus on is the 2016 engineering run, which we took at 200 nanoamps and 2.3 GeV, which is double the energy of the 2015 engineering run. And we accumulated 5.4 days of data. All right, so we have data. The 2 most important distributions look something like this. So first on the left, you have the invariant mass of the E plus E minus distribution. We're in searching for A primes, you expect a resonance peak there. And on the right, you have the reconstructed Z position of the vertex, where Z is along the direction of the beam line. And obviously we have a large number of E plus E minus pairs observed, far more than signal. So this is all background. Specifically, this is prompt background. And for our vertex distribution, we measure prompt processes with some detector resolution, which is dominated by multiple Coulomb scattering in the tracker. So more details on what these E plus E minus backgrounds actually are. Most of them consist of what we call tridents. And there's 2 types of tridents. The first are radiative tridents, and these have identical kinematics to A primes, and thus they constitute an irreducible prompt background. And you can see from the diagram here that it's the same diagram as A primes, except you have a virtual gamma there. Radiatives are also useful for providing a reference for expected signal rates, because the ratio of their cross sections is given by this simple formula. The second type of tridents are called beta Heitlers. In general, they have softer E plus E minus pairs. So if you look on the positron momentum versus electron momentum, they tend to be in this blue region here. However, they do bleed off into the signal region near the beam energy, and in fact still dominate this region over the radiatives. And lastly, we do have converted photons in the tracker and the target. However, simple cuts can eliminate about 80% of these with minimal signal loss. So with that, that's the type of data we can take. This leads us to our two types of searches. The first is a basic bump hunt, as I explained before, and we can probe these regions up here at large coupling. And what's pretty unique to us is we can search for displaced vertices in this tough to probe region here with finite but short lifetimes. And the basic principle of the search is you have some prompt background, and we measure that distribution, and we look in a region where we expect near zero backgrounds and try to capture a few events off the tail off of this exponential A prime distribution. So with that, I'll jump right into the results from the 2016 engineering run, first starting with the resonance search. So this was a blinded analysis, and which means our event selection was tuned on 10% of the full data set. And when we unblind, we get an invariant mass spectrum that looks like this in blue. And we search for bumps over this spectrum, and we find no significant excess, as you can see in this bottom left plot. In fact, we only have 2 mass points that barely get above 1 global sigma, which is obviously not significant. And we can also set a limit in epsilon squared versus mass space, and the limits are for those larger couplings, and these are consistent with several other experiments. All right, so those are results for the resonance search, and I want to focus some more time on the displaced vertex search, so we can build upon what we have there. However, we do require some extra cleanup to reduce backgrounds. And here's schematics of our 2 backgrounds that we're most concerned with. The first one on the left is the case where both electron and positron pairs Coulomb scatter in the first layer of the tracker. So this is a sort of a cartoon of the RSVT. And they both scatter away from the beam. This reconstructs a vertex that's downstream of the target and looks pretty signal-like. And similarly, we can have algorithmic issues where our tracking actually picks up an incorrect hit, where the true hit is farther from the beam than the actual hit on the track. And this can have the effect of pulling your vertex downstream of the target and also look quite signal-like. And to mitigate these effects, we have to be a bit clever. I don't have time to go into detail, but essentially we require stricter selections on the track and vertex quality for these events. And you can see sort of the preliminary effect on 10% of the data where we want to mitigate these effects out here so that we can look for a signal out here. And I should also say this search was also blinded as well on 10% of the data. All right, so once we have our final event selection, what we do is slice it up in different mass slices. So here's an example of a 105 MeV mass slice. And we fit that spectrum to a background fit, which is a Gaussian core plus an exponential tail. Then we select the Z position where we expect 0.5 background events. We call this our Z cut, and we throw away everything upstream of that. And everything downstream of that is a candidate for signal. And this defines our signal region. Now our signal, this is just an efficiency curve here. And you can see it kind of falls off rapidly at the end. And I get asked a lot why it does that. And the reasoning is due to geometrical acceptance. So there's a good cartoon here. So for a given opening angle, as you displace farther in Z, you become increasingly unlikely to interact with layer 1 of our detector. And for this analysis, we require layer 1 hits. And I'll discuss later about relaxing that requirement. But basically, that's the reason why this sort of dies at the end. So then what we do is, instead of just one slice, we want to look at the full mass distribution. And so we plot this on Z versus mass, and then we look at the full spectrum here. And this is our full 100% unblinded sample, and this signal region here is in yellow. Now, obviously, we see some events there. First, I should say we expect some events there based on the nature of the Z-cuts. We expect half a background events per mass slice. But it does appear that we see an excess at lower mass, and I'll explain that in more detail in a little bit. But first, it's reasonable to ask how much signal we actually expect. And to figure out how much signal we actually expect, we basically integrate our signal shapes past Z-cuts, and then plot that as a function of epsilon squared and mass. You can see our optimum value, which is about at 76 MeV. We expect 0.42 events. So that alone can't explain the excess by itself. However, to complete the analysis, we want to set a limit or set a procedure to set a limit. And for that, we use what's called the optimum interval method, which was developed by dark matter direct detection. And it's plotted here. And this plot is normalized such that a value of 1 is a 90% exclusion of the A prime model. And our most optimum point is at around 80 MeV, a value of 6.05. And how you would interpret that value is for an A prime-like model with 6.05 times the cross-section, we barely begin to exclude that model with 90% confidence. So unfortunately, we don't have enough data to set a limit in the canonical A prime model. However, this was an engineering run with limited data, and this is a proof of principle. And the solution to this is that we have much more data in the future with upgrades. And I'll get to that. But first, I want to discuss our apparent excess at low mass. So this was pretty recently unblinded, so these are still under investigation. So some possible background explanations are beam gas interactions. However, we're under vacuum and expect less than 1/10 of events, so that's unlikely. And what I think the more likely case is the situation where we have mistracking plus hit inefficiency effects in our detector, which might take some more work to prove and get rid of. Of course, one could also be optimistic and say, any of those can be a signal because we are sort of in one event territory. However, we're not in the business to distinguish a single signal event in this distribution. Also, it's quite unlikely, based on the table below. I basically print out the properties of these events past Z-cuts, and at least half of them have properties that are not consistent with a signal, such as a poor vertex quality or a vertex position that deviates far from the beam mean. And so what I do is plot the events selection from the previous slide and remove these events, because in principle we should be able to get rid of them. So I remove these events just for visualization purposes, and as you can see, it looks much cleaner. So perhaps in the future we might be able to get rid of these. All right, and so that's not the last step of this analysis. We have sort of 2 more steps that we can do with this. The first, or the next step we can do is explore the case where the A prime is longer lived, such that one or both of the electron-positron pair actually missed layer 1 of the SVT, and that can add some significance to our analysis. However, this does introduce more complicated backgrounds. And the next thing we can do with this analysis is explore other models, because this is a pretty interesting region of phase space that not a lot of experiments can probe. And so we want to explore sensitivity to models such as strongly interacting massive particles, or SIMPs. And the mechanism would be similar to an A prime. A primes are produced through dark bremsstrahlung. However, the A prime is prompt, and that decays into a dark pion and a dark vector, and the dark vector is long-lived, and then that would decay back to E plus E minus pairs. So it'd be a similar search, but in a lower energy regime because of the missing energy due to the dark pion. And I don't have a lot of time to go through these, so if you have questions about them,
Yeah,
I'd be happy to answer.
Matt, you have 2 minutes left, please.
Okay, I'm almost done. So the analysis from 2015 and 2016 motivated several simple upgrades. The most notable one is adding a tracking layer that we call layer 0 between the target and the current first layer, and that improves our vertex resolution by about a factor of 2. And that's really how you win this game of the displaced vertex search, is to improve your vertex resolution. So our other two upgrades I'll go through quickly. We basically moved layers 2 and 3 closer to the beam, and that improves acceptance for the longer lived A primes that I explained on the previous slide. And our last upgrade that we had, we put a hodoscope inside the vacuum chamber, which enables a positron-only trigger, which recovers events in which we lose electrons in this beam gap of the ecal there. So we installed last May and June in 2019, and here's some pictures. I think the most important pictures are these two in the bottom right, which is the case where the SVT is fully closed, which means we're 0.5 millimeter from the beam axis, and you can kind of squint your eyes and see a gap there. That's where we have to send our beam, and it's quite a challenging task for the accelerators at CBAF, but they've consistently been able to do it. This was a 4.55 GeV beam last summer with a 22 micron spot size in the Y direction directly down the middle of our detector. And once we get good beam, once we're running, as you can see on the graph below, we can collect data quite consistently. And our projected sensitivity from this data set that we took last summer using that luminosity is shown in the following plot, and we do expect to be able to probe this region here in the middle for the first time, which will be exciting. All right, so to conclude quickly, heavy photons are well motivated as a particle that mediates light dark matter and standard model matter interactions. We have completed 2 successful engineering runs. Our resonance search is now public, and both searches have exclusions that are consistent with several other experiments. Our displaced vertex search, we've demonstrated proof of principle, and you should expect future analyses with these, such as SIMPs. We've successfully completed our first physics run at 4.5 GeV with our upgrades, and this data has real physics potential, as I showed on the previous plot, and we have the possibility of running for 2021 and beyond. Thank you.
Thank you, Matt. So if there are questions, please use the Q&A section. I don't see any right now, but please go ahead. In the meantime, I can maybe ask one myself. Can you comment a little bit on the future timelines of the experiment? So you said that you ran for a couple of weeks and you had some engineering runs. So when do you expect realistically to basically complete a big fraction, if not all, of the approved beam time?
So that's not official yet. So I don't know if I want to start any rumors here. So yeah, we had 2 weeks last summer, and that was a large chunk of data. We expect to have a few more runs in the next few years. There's a possibility next year in 2021.
So sorry, maybe an easier question. How much of fraction represent these 2 weeks that you already from the approved beam time?
I'm sorry, can you repeat the question again?
Yeah, how much fraction of the total beam time represent the 2 weeks that you already run?
We're expecting 180 days of running total. And so we have 2 weeks from last summer, and then we have about a week from the engineering run. So percentage, that's, I don't know, 10%, 15%.
Okay, thank you. Let's see. I don't see any questions on the chat section. So thank you very much again, Matt.
All right, thank you.
We'll move to our next speaker, who is Ian Nguyen from JLab, who will be talking about how exciting it will be to have a helium-3 target in the class 12 detector. Ian, go ahead.
Can you hear me?
Yes.
Okay, like I will share the slide now. Let me see where I can do that.
It's on the right-hand side. It looks like the Windows picture icon.
Window picture icon. Let me see. I still don't see it yet.
On the right?
Mm-hmm. On the right. Okay, I see that. Yep. Can you see my screen now?
Not yet.
Mm-hmm. Yeah, can you see my screen now?
Oh.
No. When you click it, make sure you select entire screen.
Mm-hmm. Yeah, can you see it now?
No.
No, still no. Oh, why is that? Okay, I think I need to log in again. Sorry for this.
I can try to share your slide myself if that doesn't work for you.
Yes, let's do that. Let's do that, Carlos. If you have those slides up, let's just have you share the PDF, and then you speak to that. Remember to give him an advance every time he needs to advance the slides.
I will try one more time. Let's see. It will be easier for me to do that myself. Yeah. Why is that?
Something coming, but we don't.
Hello, can you hear me now?
We can still see you and hear you, but let me try to.
Okay, can you?
Yeah, let me try to do that.
I can still not share the screen yet. Yeah. Oh, is it bad?
Okay, so can you see my screen?
Yes, I can see your screen. Yeah.
Okay, so you can go ahead and just tell me when to switch slides.
Yeah, sure. First of all, I want to say thank you very much for invitation, so I can give the talk today. It is a great opportunity for me to give introduction to you about two new proposals we just submitted to the PAC 48. One is spin-dependent polarized helium-3 target, and another one is precision measurement of A equal 3. Next slide, please. So for the first and the next as well. So for the first polarized helium-3, we win for the polarized helium-3, we want to measure. Can you next slide, please? So we want to do the longitudinal spin dependent DIS using DIS and semi-DIS. And we want to focus on the PT dependent of the neutron longitudinal spin structure and nuclear correction to the DIS process. For the second proposal, we are using quasi-elastic on A equal to 3 to measure neutron form factor, field body, the nuclear structure, and the SRC. Next slide, please. So let's go into the detail of the first proposal on the polarized helium-3 in class 12. We want to discuss about two main points: is the target conceptual design and the physics overview. Next slide, please. So first, I wanted to mention about the context of this proposal. First, we attempt this proposal to leverage the recent technical advance by the BNL and MIT collaboration in the high field matter stability, the optical pumping called the MIOF for the polarized helium-3. So second, we want to make use of the double cell cryo target, what was successfully using at MIT. So by combining these two technical, we were able to locate the polarized helium-3 target in the 5 Tesla central solenoid of the class 12, and we able to achieve the class maximum luminosity. We want to require for 30 part days to study longitudinal on the neutron structure. We just want to emphasize that the measurement we want to propose in this experiment is complementary to the approval ND3 class program, and it also complementary to the ongoing and planned COPS experiment and can strengthen the case for the proposal solid detector. Yeah, next slide, please. We want to talk more about polarized helium-3 target. It plays very important role for the long term in the nuclear physics because it is the unaffected polarized neutron target. That is why it is very crucial for study of the neutron spin structure. On top of it, it is a light nuclei. So it can be exact calculable. So it can be used to the bandmass theory calculation. So polarized helium-3 was used in the many experiments in the 1980s, but all of these polarized helium-3 are the low magnetic field target. Next slide, please. To get to polarized helium-3, one of the techniques we use, the traditional technique is using spin exchange optical pumping, COP. This is very successfully used in the SLAC and the JLab 6 and the 12GV program. But this traditional target never used in the hobby. And with additional technical difficulty on the 5 Tesla of solenoid of the class 12, this target is not available to use in the class 12 at this point. We have another technique called MIOF, like I mentioned before. So this one was successfully used before, but it have a limitation because of the low pressure and low density. But with the new development, now we have a high magnetic field operation of the MIOF. So next slide, please. So now, with this new development, the MIOF, the target, can operate with the much higher pressure, 100 times higher, and 100 times higher. And recent work showing that the MIOF can run with 100 microbar and can reach to 50 to 60 polarization, 60 to 50 polarization, and it can run at the 5 Tesla magnetic field. The next slide, please. Oh, this is not good. So with the development of the MIOF, the target, and with the target concept design for class 12, we combine between the MIOF target and the double cell cryo. So this combination will increase the target density by 6,000 times. That is why we can reach the target maximum luminosity. And the more detail of this target concept can be found in this reference. But in the next slide, I can show you the current design of this target. Next slide, please. So this is our current proposed target design. As you can see that on the left, we have a glass pumping cell at the room temperature. So helium-3 will be polarized in this glass cell, and then it will pump to the other cell, is the aluminum cell, at a much lower temperature. The next slide, please. So at this point, both the technique and the design for the target are available. So we only need to build it. We only need to build it and do the testing. So this development is leading by the J. Maxwell, which is supported from the JLab target group, Hope B, and the Richard Miller MIT group. And we have a confidence that with this development, we can bring the target design to realization within the reasonable amount of time. Next slide, please. So after we have the target, we will able to put the target to the class 12 solenoid, the central solenoid detector. Next slide, please. So this is our running assumption. This is our running assumption. We will run in the 10.6 GeV with beam, and we will request for 30 days for the precision measurement to study the transverse momentum dependent TMD parton distribution. Next slide, please. Yeah. I don't know who is moderator, but I'm using the chat to coordinate with you better, so you know when the next slide better. So to study the TMD, we use the semi-DIS measurement. So this is a diagram. So this is a diagram of the SIDIS channel. So you can see the lepton in and the scattered out. And the PT is hadron transverse momentum, and the KT is the quark transverse momentum. So this proposal, we have a very high precision in the 5 dimension on the different variable and very wide kinematic coverage. And especially we have a PT up to 1.3 GeV. So by measuring the PT dependent, we were able to have access to the KT dependent. And as you can see in this table, we have a different function to do the measurement, but we only focus on second row of this table to do measurement on the G1 and the A1. Yeah. So the next question we want to address is the spin and the flavor dependent of the KT. So these two plots on the left is showing the calculation. So the bottom one is showing that the KT dependent of different flavor U and D, they are strongly dependent on the KT. And on the top plot is showing the fraction of the quark transfer momentum aligned with the nuclear momentum. This fraction also heavily depends on the KT. So in this measurement, we want to do measurement on the ALL and the AUL. These two asymmetry is a combination of the different functions that depend on both I and KT. So by measuring the ALL and AUL, we were able to have access to the KT dependent of the polarized quark. Next slide, please. Are you still hearing me?
Yes, we are reaching slide 18.
Yeah, okay. So the next question.
I wanted to let you know that Carlos can't see the chat when he's sharing the screen, so you will just have to say out loud when you want to change slides.
Oh, okay, sure. Yeah. So the next question we want to address is nuclear correction. So as we know that helium-3 is a nuclei, so we want to use helium-3 to study the medium effect in the SIDIS process. So this medium effect, they will be different with the ND3. So by combination of the both data set, we will put much more the constraint on the calculation about the medium effect on the SIDIS process. Next slide, please. So based on that, the three questions we want to address that shape up the proposal, the physics program as listed here. And we also have a much more the future, the physics opportunity on the deep virtual exclusive process, the task EDIF, or transversely the polarized target or the quasi-elastic. Next slide, please. But for this proposal, this is 2 points as our focus physics program. Next slide, please. So to able to do the rate estimation, to do the projection for this proposal, we are using the first full reconstruction change of the simulation. So we use a class 12 GIF to generate the event and pass it through the full GMC and do the reconstruction. For the projection, we are showing the asymmetry absolute uncertainty. For this absolute uncertainty, we correct for dilution factor and the polarize of the target and the beam. Next slide, please. For this proposal, we are using the log binning of the EIC. And as you can see from this slide is that with this verified binning, we still have a really good statistic uncertainty. It is sub% level. Next slide, please. So for this high precision statistic, we were able to have projection measurement for PT up to 1.3 GeV. And as you can see in this projection is the ALL for different beam of the Q square. We think that this measurement is really important because it's providing the access to spin and flavor dependent of the KT distribution in the valence quark. And with the Q square dependent, this measurement will give us a test of the validity of the underlying theory we are using in SIDIS process. Yeah, next slide, please. We also can do the very high precision measurement on the X dependent. As you can see that in this one, the statistic is very significant to determine the different dependent. And for ALL, the data, this one will provide the input, a very important input for global analysis of polarized PDF. The next one, please. The next one we want to do the measurement is the AUL. So for this AUL, as you can see on the right side, the formula AUL is a combination of the two other functions. So by measuring the AUL, we can have access to transverse the polarized quark in longitudinal polarized of the neutron. And the AUL also gives us an access to column fragmentation. And from the projection plot, you can see that we also have a very high precision for this measurement. Next slide, please. So with these three, the projection, the main projection, the measurement, I want to summary the polarized helium-3 proposal. So we asked for 10.6 GeV for the 30 pack day. And for this proposal, we will determine the spin dependent to the DIS and semi-DIS with very high statistic precision, cover the unmatched kinematic range as well. And from this proposal, we will able to study the nuclear correction to see this process. So now we go to the next slide to study about the other proposal on A equal to 3. So with this one, the next slide, we are study EE prime P. Next slide, please. So this, we will use EE bright to study the neutron form factor using the ratio of helium-3 to tritium. This one was measured in the whole A before, but it have very limited Q coverage. But now with the class 12, we have a much better the Q square coverage. We can go to the really low value of Q square with very high precision, as you can see in the projection plot. So with this data set, we can put a much more constraint on the calculation at the low Q square region for the neutron form factor. Next slide. Next slide, we will use the EE bright P measurement to study about field body nuclear structure. So this study, we did it in whole A as well. And the measurement, the data were compared to the data to theory calculation. And we were able to benchmark the theory calculation up to 500 MeV with the good agreement. So this is a very high impact result, and it was published in the PRL as the editor suggestion a few weeks ago. The measurement is very important, but it have a limitation because it have a low statistic and the coverage of the PT. So now with the class 12, we have a 10 times more statistic and much larger kinematic coverage. So with this one, we can do this measurement is much better up to the 1 GeV. And the next one we want to do measurement is the EE bright PN. Recently, there are another paper using classic data were published on the Nature and using the GCF factorization cross-section approximation using the different NN interaction. So we want to able to test the different NN interaction. So the data from A equal to 3, it is exact calculable. It can be used as a precision test for the to end the interaction. In the next slide, we have initial design for the tritium target to put it in the whole B. What can satisfy every safety requirement. So this designs were made by Dave Meakin. And in the next slide, we are showing. So in the next slide, this is the requirement for the beam time for A equal to 3. The measurement, we will need about 60 days beam time to do our physics program. So we think that both experiment, both proposal have a very excited the program, and we believe that we can deliver the really high impact result in from these two proposal. So that is everything I have for today, and I'm sorry for the technical issue. And if you have a question, please let me know. Thank you.
Thank you very much. Yes, there are at least 3 questions I can see.
Mm-hmm.
So let me start with Todd Everett, who is asking, how will you measure the absolute polarization of the helium-3 in the beam, and do you expect any beam depolarization?
Yeah, I think for this question, I need to address it to the Jay Maxwell. He is the leading for the target expert of this project. Yeah.
Good. James, are you there?
Just promoted James. He'll be over in a second. Go ahead to the next question, and we'll come back when we see him on.
Okay. The next question is by Sebastian Kuhn, who asks, you state that the measurement will yield a high precision data for inclusive A1 on helium-3. How does this compare to the existing whole A1N experiment?
For this one, we have there are 2 different here. According for the whole AC, they have a higher luminosity than us. But we have a much bigger the coverage range in the both H and Q square. And I think that with our position, we already have a very good statistic uncertainty for it. And on top of that, the A1 is not top priority measurement for it. We are more focused on the CDS measurement, and A1 is like production measurement for it in this proposal. Yeah.
So is James already?
Hello, can you hear me?
Yes, we can.
Oh, very
Go
good.
ahead.
Yeah, so I see a couple of questions in the queue for target-based stuff. So the first question was, how do we measure the absolute polarization of the helium in the beam? So we'll be taking a cue from the MIT Bates 8802 target in this respect, in that essentially the way they measured it was they measured in the pumping cell the polarization, and essentially inferred the polarization in the target cell based on the rate of relaxation they expect and the rate of transfer the gas between the target cell and the pumping cell. So we can measure the pumping cell polarization using a probe laser to take a look at two different metastable states in the plasma. And so essentially we'll infer the polarization in the target cell based on the polarization in the pumping cell. If it turns out that this is not going to give us enough accuracy, we also have plans to take a look at pulse NMR systems, measure the polarization. But I guess his next question in there was, do you expect beam depolarization? Yeah, so the ionization from the beam will create diatomic helium in the gas. But we've got a paper from 1988 that shows that as the magnetic field increases, the relaxation from these diatomic molecules drops precipitously. So I think this is something we really want to test as we go in through the target development process. But right now we think that because the field will be high, the relaxation due to these diatomic helium should be low.
Okay, thank you very much. I see there's also a question by Nilanga, but who was partially answered by Dag. Maybe you can guys answer in writing. The topic, because we need to move on now. Maybe a quick question, maybe by Jane Pin. Question on dihedron projection versus solid in your backup slide with a factor of higher than 20 lower in luminosity. Is it possible to have the projection higher over the Q-square range?
So can I see the question from JP? Let me see. Yeah, in the backup slide, and let me read the question. Yeah. Oh, yeah. So for that projection, we already scale up with the luminosity of the solid based on the number we get from the email exchange with you, JP. So so we use the solid the luminosity already in that projection plot. So I think that the thing it makes the dihedron projection, the class 12, it have a much better statistic, is that because we have a bigger acceptance in the class 12 compared to solid, because solid only have a forward detector. So I think that's the reason. It's not because of we use less luminosity for solid.
Okay, I think we should move on. Thank you very much again, Diane.
Yeah.
Our next talk will be by Stefan Diel, who will be reporting on SIDIS single pion and dihedron beam spin asymmetries measurements with class 12.
Yes, hello everybody. Can you hear me?
Yes. Please go ahead. We can see your screen.
Yes.
Yep,
so
perfect. Just hide the little banner in the top, if you don't mind.
Yes.
Yep, perfect. Go ahead.
So I will talk about SIDIS single pion and dihedron beam spin asymmetry measurements with class 12. So our general goal of these measurements is to get a deeper understanding of the momentum distributions inside the nucleon, and these momentum distributions can be described by three-dimensional transverse momentum distribution functions, shortly TMDs. And as you can see, these functions depend on the longitudinal momentum fraction x and on the transverse momentum component kt. And with class 12, we can access the TMDs with semi-inclusive deep inelastic scattering, SIDIS. And there are two types. On the one side, we can study single hadron SIDIS, where we detect one pion, or one hadron in general. And we can study dihedron SIDIS, where we detect two hadrons. So let's start with the SIDIS single hadron cross-section for an unpolarized target, which we had in our study. And here you can see this cross-section displayed. And as you can see, it contains several model-independent structure functions, FUU and FLU. And it depends on the angle phi h between the leptonic scattering plane and the hadron production plane. And for the beam spin symmetry, our variable of interest is the structure function FLU sine phi. And when we have a closer look into this, we see it contains several TMDs and fragmentation functions, like the twist-3 pattern distribution function, the Collins fragmentation function, the unpolarized distribution function, the twist-3 T-odd distribution function, and the Bohr-Mulders function. So in total, we have a convolution of 4 TMDs and 4 fragmentation functions. And we can see that each term contains a twist-3 component. So in total, it's a twist-3 variable. And the results from this study can be nicely used in global fits to constrain these TMDs and fragmentation functions. And additional constraints can be also obtained from the dihadron SIDIS. Here for dihadron SIDIS, a special feature is that the PDF E of x is coupled only to the interference fragmentation function H1, which we can see here in the definition of FLU sine phi r. And as therefore the final state electron pi plus pi minus x provides a relatively clean access to this TMD E of x. And E of x is a very important quantity since it's related to the scalar charge of the nucleon and to the pion nucleon sigma terms. And in addition to this, the dihadron SIDIS also allows the study of defragmentation functions with no single hadron analog, like for example G1 perp, which describes the azimuthal dependence of an unpolarized hadron pair on the helicity of the outgoing quark. But let's start with the experimental setup which we used. So the data was recorded with class 12 in Hall B during the fall of 2018, which I used for this study. And there we had a 10.6 GeV electron beam with an average beam polarization of 87% interacting with the liquid hydrogen target. And the analyzed data corresponds to approximately 20% of our approved run group A beam time. So then let's come to the particle ID. Here our electron ID is mainly based on the electrokinetic calorimeter and the Cherenkov counters. The hadron ID is based on the beta versus momentum correlations from the time of flight system. This beta versus P plot is shown here for the example of positive hadrons, where we can nicely see the pions, kaons, and the protons. And to identify them, we use a maximum likelihood particle ID, where we assign the particle to the species with the highest probability. And in addition, we check if the particle is within a certain confidence level. And finally, so for the photon identification, we mainly use the electromagnetic calorimeter. Then let's continue with the event selection and the kinematic cuts for single pion SIDIS. Here first for the phi 0 selection, we require that the photons have more than 600 MeV of energy, and we require that we have an angle between the electron and the photon larger than 8 degrees to reject radiative photons. And if we now consider all 2 photon pairs, we end up with the invariant mass of the 2 photon pairs shown on the right plot. And here we can see that we get a nice pi 0 peak where we can place a 2 sigma cut around the peak position. And we can use sidebands in the left and the right side of the peak to get the background asymmetry and to subtract it later on. In addition, for all pions, we use an additional set of cuts. First, we require that the electron momentum is approximately larger than 2.1 GeV, which corresponds to y less than 0.8. And we require a minimum pion momentum of 1.25 GeV. Then we place the deep inelastic scattering cuts, q square larger 1 GeV square, w larger 2 GeV. And we cut on the final state hadron momentum fraction, where c has to be larger than 0.3 to remove the target fragmentation region. And in addition, we place a cut on the e pi x missing mass to remove exclusive events. When we look, for example, in the e pi plus x missing mass shown on the right, we see it in the upper plot for small pt and in the lower plot for large pt. And we see especially at large pt, we get a very dominant contribution from the exclusive neutron peak. And to reject this, we place a cut on the missing mass larger than 1.1 GeV. Then on this slide, you can see the kinematic coverage for pi plus. It's very similar for pi minus and pi 0. Here on the left side, you can see the correlation between Q square and W, where we can see that Q square reaches up to 1012 GeV square. And in the lower plot, you can see the correlation between Q square and X, which are strongly correlated. And the red lines represent our DIS cuts, which we place on it. On the right side, the figures show one-dimensional projections of our main kinematic variables, Q square, X Bjorken, C, and PT. And here we can nicely see that the experimental results shown as a blue line nicely agree with our Géant-based Monte Carlo shown as the red dots. Then our goal for the single Pion SIDIS is to extract the structure function ratio FLU sin phi over FUU for the single Pion beam spin asymmetries. And to extract this, we substitute the terms in front of the phi dependence of the cross-section by the three moments AU cos phi, AU cos 2 phi, and ALU sin phi, as you can see it here. And based on this, we can nicely define the beam spin asymmetry with this expression, where we can see that the leading order contribution is coming from this ALU sin phi times sin phi term. And when we connect this to the original cross-section, this is done down here, we see that ALU sin phi is directly correlated to the ratio FLU sin phi over FUU just by this kinematic factor here. So we can directly transform it. And in the past, measurements of these quantities have been performed already with GLASS, Hermes, and COMPASS. But the significant advantage of class 12 is that we have a significantly higher statistics and that we can cover an extended kinematic range in Q square and PT. So then let's come to the experimental results. Here we see the experimental definition of the beam spin asymmetry with the beam polarization PE, which was 87%. And when we look on the beam spin asymmetry as a function of phi, for pi plus in the upper row for C binning and in the lower row for Q square binning, we can see that it can be nicely fitted with a sinuate shape over the complete kinematic region in Q square and C, and also in the other variables. Then let's look in some one-dimensional results first for the structure function ratio FLU sin phi over FUU. So the first row shows the results as a function of C, and the first column for pi plus, in the center for pi minus, and on the right side for pi 0. And for C, we can nicely see that for pi plus, we get an increasing trend with C. The black points show the recent class 12 results in comparison to the previous class study from 2014, which is already published with the red points. And for pi minus, we see we have some negative values, which are also increasing for class 12, falling for class. And for pi 0, we again have positive values. So we see in most of the kinematic regions, both experiments agree, but not everywhere, especially for pi minus. And the reason for this is that we integrate over the other variables and we have different kinematic ranges and distributions for both experiments. And therefore we expect some disagreement, and to understand this, we really have to do a fully multidimensional study where we do not integrate over one variable, which I will show later. When we look into PT in the lower row, we see again, when we look, for example, into pi plus, that for small PT, we get a value close to 0, then it increases, we get some plateau, and for high PT, it starts to increase again. And we can also see overall that we get a relatively good agreement within the error and fluctuations with the class data. Then we can have a look also in the X Bjorken dependence and in the Q square dependence in the upper and lower row. And we can again see for pi plus, we have positive values, pi minus is negative or close to 0, and pi 0 is again positive. And when we have a look on the lower row for Q square, we can nicely see how our statistics improves and also how our kinematic range in Q square improves compared to the all class data. So this is a completely different dimension in terms of data quality and statistics. So from the theoretical side, there are already several predictions for the 12 GeV JLab data. Here you can see a prediction for ALU sin phi, which is the most advanced for Mao and JLUO. It's for pi plus in the upper row and pi minus in the lower row for the C dependence, the X dependence, and the PT dependence. And when we compare these red lines with our results, we can get out that they reproduce several characteristics of our results, like the increase with C for pi plus and others, but they reproduce not everything. So this still has to be adjusted to our real data. And updated calculations from different collaborators are already in progress, and also the multidimensional binning, which I will show now, will enable a much better comparability with these calculations. Since in the 1D binning, it ever has to integrate and make some assumptions for the integration. Then let's come to the fully multidimensional binning, which is shown here. Here we see that with the available statistics, we have seen a fully multidimensional binning in Q square, X Bjorken, C, and PT becomes possible for the first time. It has never been done before. There are only at least maximum two-dimensional binnings. And for this multidimensional binning, we first look into the electron variables, Q square versus X Bjorken, where we see that they are nicely correlated. And based on this plane, we can select 16 bins in the Q square X Bjorken plane, which you can see here. And for each of these 16 bins, we can select up to 7 times 7 bins, rectangular bins in the CPT plane. So in total, we end up with 583 bins times 12 bins and 5 for each of these bins. So we have more than 7,000 beam spin asymmetry bins in total. And as an example, I want to take pi plus and have a look into the C dependence for increasing Q square and fixed X Bjorken. So we look into bin 12, bin 13, and bin 14 in the three figures. And when we look up here in the Q square versus X correlation, we see bin 12, 13, and 14 have a fixed X between 0.4 and 0.5. And they have increasing Q square from 12 to 13 to 14. And here we see the C dependence of FLU sin phi over FUU, and the different colors represent different PT bins, which are shown here in this small box between 0.15 and 0.65. And we see for small c, we have a nice increasing trend for all PT values. For small q square, when we go to a higher q square, we see there is some saturation at high c. And when we go to the highest q square in the right plot, then we see that for small PT values, shown by the black, red, and green points, we even get some drop for high C values. And this shows that with this multidimensional binning, we can nicely disentangle different effects which we expect in the different kinematic regions. As a next example, I want to show the Q square dependence for pi plus. Here C is fixed between 0.3 and 0.4. And we look into different PT regions for the different plots. The first one is 0.2 to 0.3, and then it gradually increases up to 0.5 to 0.6 in the lower right plot. And here we see the Q square dependence, and the different colors corresponds to different X Bjorken ranges, which you can again see in this small box. And since Q square and X Bjorken are strongly correlated, also these colored points are strongly correlated. So for each X Bjorken, we can only cover a small region in Q square. And we nicely see for small PT, it starts to increase slightly before it saturates. And when we move to the highest PT value in this lower row, we see this increase with Q square is much stronger first. And then we see it saturates, or we even get some indication for a drop with Q square at high PT. But the statistics is not sufficient to say something final here. Then, as the last point of my presentation, I want to come to the first dihedron SIDIS results. Here we have looked in the final state with two charged pions, so electron pi plus pi minus x. The kinematic cuts which have been applied are shown here. They are mostly very similar to the single hadron case. We only require a different C cut, a cut on X Feynman, and a cut on the missing mass, which is a bit higher. And based on this data, a simultaneous fit on all three modulations was done. Since for the dihedron SIDIS, we do not have only one sin phi modulation, but we have now three modulations. a sin phi r modulation, a sin phi h minus phi r modulation, and a sin phi h modulation, where we have two angles, phi r and phi h. And phi r is the angle between the leptonic scattering plane, which we can see here in white, and the difference between the two meson vectors. While phi h is the angle between the leptonic scattering plane and the sum of the two meson vectors. And these combinations produce different correlations and modulations. And here we see an example for the ALU sin phi r modulation as a function of phi r for a fixed small x Bjorkenpin. And we can see that also this can be nicely fitted with the sinuate shape as expected. Then let's have a look into some first results. Here we see in the left plot the ALU sin phi r modulation as a function of x. And we can nicely see that we get a significantly positive value, which was also predicted by theory. And this is very interesting since this modulation ALU sin phi r is directly sensitive to the Padron distribution function E of x. On the right side, we see the ALU sin phi h minus phi r modulation as a function of the invariant mass of the pion pair. And here we see it's first positive, then it starts to drop around the rho zero mass, and then it's negative, it has a sign change, and then it increases again. And I think this was not predicted like this by theory, so it's very interesting to study this effect. And it's this variable, this modulation is also of interest since it's sensitive to the G1 perp defragmentation function. So then let's come to the conclusion and an outlook. We have seen that class 12 enables the extraction of SIDIS pion beam spin symmetry moments with high accuracy in an extended kinematic range. We have seen that FLU sin phi over FUU is positive for pi plus and pi 0 and close to 0 or slightly negative for pi minus. We have seen that the d-hadron beam spin symmetry in phi r shows a non-zero value of ALU, which is very promising since we may be able to extract E of x from this data. And we have seen that the fully multidimensional analysis of the single pion SIDIS enables the decomposition of different effects in different kinematic regions. And finally, altogether, we can say that the class 12 SIDIS results will significantly improve the results from global TMD fits. And they will also provide us access to so far poorly known TMDs and fragmentation functions. Thank you.
Thank you very much, Stefan. Nice overview. So we have a question from Yan Ping, who is asking about your single pi 0 data. He says it is surprising to see that FLU is high at low x and then drops at high x. And does it imply there is a significant non-protonic effect?
Yes, so I have to mention to this that this is preliminary data for pi 0 since we are still studying the exact impact of the background for this. So it might be that it goes a little bit down in the final results. So we should not interpret too much.
Okay. I don't see any other questions, so in the interest of time, I think we should move to the next talk. Thank you very much again, Stefan.
Yes, thank you.
So now we will move to the last talk of the session. Thea Keppel will be telling us about parton distribution functions at large X and results from JLab 12. So Thea, please go ahead and share your screen. We can see your screen already. Yes, just go full screen and then hide this little banner at the top. Don't mind.
All right. I think you should be there. Can you see it okay and hear me okay?
Yes, perfect. Go ahead.
All right. So I get to combine a few new results that fall under the umbrella of getting a better picture of PDFs at large X. And large X, of course, is the valence regime of the nucleon. So we can first ask ourselves, if I could change my slide. Oh no. Okay.
I think you need to click on the
I got it. I got it. Yep. So ask ourselves why the valence regime is particularly interesting. So viewed one way, you could say, well, we know a lot about it already, but viewed another, it's absolutely critical to study it. The partonic structure in the valence regime completely, maybe other than the mass, defines the hadron. It gives us the baryon number, the charge, the flavor content, the total spin. And so these come from the valence partons, the partonic structure in this valence or large X regime. And so this regime becomes a keen discriminator of our various nucleon structure models. Moreover, the valence regime at large X and low Q evolves. These parton distributions are what we evolve to low X, high Q. And so it sits at the intersection of particle and nuclear physics, where we can evolve from one regime to another. And so we need to understand the valence regime in order to understand really the very high Q, low X regime dominated, for instance, by gluons. So here are pictures of how well we understand these PDFs at large X, and you could pick any PDF set available on the market now. I kind of randomly just picked a few, and these aren't necessarily new, but the status hasn't changed. Here's a HERA PDF, here's the neural network PDFs, here's MSTW, this has CTEC, and whichever one you pick is going to have this kind of characteristic shape that as you go up towards large X, and this is even only 0.8, the uncertainties blow up, and this is on the down. This is on the glue. It's true for every single PDF that this large X valence regime is not well known. So here's an example of what I was saying before, where it's also this regime is also a keen discriminator of nucleon structure. And so I won't go through this whole slide. I think for this audience, you all will understand the point pretty quickly. I can write down the wave function of the proton in terms of valence partons, and with particular structure, I can write it polarized, and then I can take this thing and now I can make different assumptions about what the structure of this nucleon is. So I can say in a simplistic picture, I have SU6 spin flavor symmetry, and then I can immediately write down that D over U should be 1/2, and the neutron to proton, neutron being dominated by D, proton being dominated by U, is 2/3 as X go to 1. But we know that that's not right. We have N delta mass splitting, so I can say, okay, I have a different weight between the S equals 1 and the S equals 0 states, and I can come up with a different model that would tell me that the neutron to proton or the D to U ratio would be either 1/4 or 0. Or I can invoke hadron helicity conservation, which would give me yet a different approach. Or I can put in a Dyson-Schwinger, which gives us a finite size S equals 0 and S equals 1 diquarks. And I get a different result. And there are many more. And so this is the subject of numerous review articles. And it's been a long-standing problem for quite some time, kind of the flagship issue for valence PDFs at large X. And so this is just a smattering of the different theoretical predictions, which are really speaking to the fundamental nucleon structure. So, okay, we have theory, we need a measurement. But measurements have not been easy either. Deuteron effects are an obstacle. So we want to get at the neutron. We don't have any free neutron targets. And so we use deuterium, but depending on our deuterium model, we can get an array of answers for what happens for F2N over F2P at large X. And I'm sorry, I didn't say it, but F2 is the structure function. So this is measured in inclusive scattering from deuteron, pulling the neutron out. And so these are data from SLAC analyzed that way, but with different deuteron models. So this is kind of a famous problem. And so where we sit is that N over P, and so D over U is essentially unknown at large X. We have conflicting fundamental theory pictures. We have inconclusive data due to deuteron nuclear corrections. And so this translates to those large uncertainties on the D and G in the PDFs. So we need a new generation of experiments at JLab focused on high X. And so happily, that's where we are, is where the first generation of experiments has run. So that's what I get to talk to you guys about. One of the first was the Hall C 12-JeV commissioning experiment. It was one of a suite of experiments to commission the super HMS spectrometers. And the idea was to reduce the uncertainties in F2 proton and F2 deuteron. Aside from the theoretical issues with the deuteron, one can take a look at the quality of the data at high X. And so what you're looking at here, this is the standard. Can you guys, I hope you can see my cursor. This is the standard Q squared.
Yes, we do.
Good, thank you, Carlos. This standard Q squared and X type scatter plot of where the kinematics were obtained. So this big green region in slack looks like, oh, we don't really need to do this, but you need to look over here where this is Q squared and this is X, and these arrows are indicating the range that we measured with the 12-JeV Hall C experiment. But you can see the uncertainty on this vast amount of green slack data compared to the 6-JeV JLAB data, and then the range of the new 12-JeV experiment which is expected to have uncertainties like that, down around the 2% or better level. So we can also provide better measurements as well as hopefully better deuteron theory. So this is just a picture of the HMS and SHMS, and in order to do these measurements, we actually needed to have an array of angles and spectrometer momenta. So this is just a picture of how close these two spectrometers can get. You can see the downstream beam pipe going through the spectrometer magnets here. So nice use of the SHMS really pushing it, which is why this is a commissioning experiment. And so these are some preliminary data. Actually, the publication is being drafted within the collaboration. This is the deuteron to proton structure function ratio, which from which one may extract the neutron to proton for different angles of the spectrometer, which define different Q squared ranges. And so you can see already right off the bat some things like this old fit that was used by CERN, F2LM, really is not describing the valence regime well. And that's okay. It's not a hit on them. It wasn't really meant to, but it is a little bit of a caution because I see people use this, for instance, sometimes for isoscalar corrections. But more interestingly, we could maybe differentiate among these more modern PDF-based fits and look at that. So I'm going to zoom in my magnifying glass onto just this one here to give you a feeling for the kind of power that this data set might have. So this is Kulag and Petty and CTech Jefferson Lab, so two of the different PDF fitting efforts and how well the curves are going through here. And then interestingly, this KP hybrid also tries to include the resonance region because, of course, as you go up and up and up in X, you invariably come into the resonance region. And there are now efforts also from Eric Christie to include the resonance regime in these global PDF-based fits. So that's a nice thing. We need global framework with the deuteron corrections all incorporated to try to get out the neutron. The status of this data is that it's, as I said, working towards a paper just beating down the final systematic uncertainties. But one shouldn't take away from this something like, oh, you know, this green model looks better than this yellow one. That's not really the point. The point is to include these type of data in these very large global fitting efforts because the parton distribution functions are best extracted utilizing QCD evolution, utilizing collider data, utilizing Drell-Yan type data, utilizing deep and elastic data, all in a full framework, QCD framework to extract out the PDF. So this is just one piece. This is an example. I want to say something about the effort here at Jefferson Lab. This is the CTech Jefferson Lab CJ fits, where you can see the characteristic uncertainty at large X. But this is one of just a couple efforts that is optimized for the valence regime. And so really trying to extract the PDFs in the valence regime, which is difficult. It means that you have to incorporate higher twist and target mass corrections. You have to allow D over U to go to a constant, even though D and U individually have to go to 0 at X equals 1. You have to allow that ratio to go to a constant. So all of these things are not standard for the high energy physics type PDF extractions. And importantly, you need accurate deuteron corrections. So here's where this data comes in. So this is the triangle, for instance, for the down PDF. So we look at deep and elastic deuterium, which I just showed you from Hall C. The plus to it is that there's a large body of data from multiple experiments around the world for decades. So there's a wide range in X and Q squared and nice precision data. The problem, as we said, is that it requires deuteron nuclear corrections. We have also W asymmetry data from, for instance, the Tevatron, D0 and CDF, and also coming up from Brookhaven. And these have direct sensitivity to the down, and they're at high W and Q, but it's a very small data set, a dozen points or something like that. So it can be a pin, but it's not going to have the broad power that the deuterium does. So what you want to do is try to link these. So at JLab, we also have BONUS, which provides a nearly model independent neutron target, and I'll talk about that a little bit. And there is current data from the 6GeV era, but that data is small set and low W, low Q. But as you can see in this triangle, each of these data sets provide us a different piece of information, have pros and cons, but the sum is greater than any one of the parts, and provided all together, we can extract the D distribution. So this Hall C data is going to be very crucial here. How crucial, you might ask? This are preliminary results from CJ looking at the impact of this data set on the PDF uncertainties. So this is the D to U uncertainty ratio, and this is the gluon. And so you can see, for instance, standard, and then this is the experiment number for the Hall C. And so we're going to improve on the uncertainties within the context of a global fit that has deuteron nuclear corrections and has other information that would help us be sure that we're not only dependent on those things like an accurate D from a collider experiment. Okay, so that's what I was saying. Sorry, the whole is greater than the sum of its parts, and we move on. So I just wanted to say something quickly about the BONUS experiment, even though it's not quite the focus of my Hall AC talk, but just to point out that this technique is another way of getting at the neutron. Maybe you've heard about this. I hope all of you have heard about it already. So we take a deuteron, but you tag the proton. So you have a deep inelastic event off the neutron, but it's a tag deep inelastic event. You ensure that you hit the neutron by measuring this recoil proton here. And that's tricky business, and you can read about it in any one of these papers from the 6GeV era, but we were able actually to go up to high X, but not quite really high enough, and also in the resonance region and not high enough Q squared, but it was still powerful for global fitting efforts. This is from Kulag and Petty's paper, where they point out that the recent BONUS data actually reduced the uncertainty in constraining the overall nuclear corrections, here meaning the deuteron corrections. So we're really, really getting there. And of course, BONUS 12 is now poised to run. This is the new RTPC being installed in class, and some some events, in the TPC from that. So BONUS 12 hopefully will provide us with some clean neutron data. But another approach you can take is entirely different. You can take a nuclear physics approach and say, okay, our problem is that the deuteron experiments present a free nucleon extraction complication. We can't get the neutron out of the deuteron. So what should we do? Add more nucleons. So actually, the trick here is to take the tritium to helium-3 ratio to get that F2N over F2P quantity. And that will actually minimizes nuclear physics uncertainties. How does this magic happen? Well, you can look at the nuclear effects in helium-3, and the nuclear effects in tritium, and then form a super ratio of these. And if the nuclear effects in helium-3 compared to the nuclear effects in tritium are not that much different, then one can extract the F2N over F2P by leveraging this super ratio effect. So it really relies on the difference in the nuclear effects, which are calculated by various theory groups. So we deployed a tritium target in Hall A little bit ago, a couple years ago now, very first installation. And this was the first tritium target used for our field in decades, actually. So that's quite exciting. We have tritium again, and I understand people will be proposing again to the PAC for more tritium. So this was a success in many ways. It leveraged the high JLab luminosity, meaning we didn't have to use as much tritium, so quite a safe target. Here's a picture of the lovely target, the heat exchanger, the tritium cell, and then cells also for the helium, deuterium, hydrogen, and empty targets and nuclear targets along the bottom. So the kinematic coverage of this experiment, the experiment looking to measure F2N over F2P was called Marathon. There were other tritium experiments, which I don't have time to talk about, unfortunately. But the Q squared and X coverage, very nice for these to match the valence regime and where we have uncertainties in the PDFs from the global fits. And these are preliminary results. This is the actual data, of course, tritium-3 to helium. We can also look at tritium to deuterium, helium to deuterium. Because we also measure hydrogen as a normalization check and deuterium. But we can now leverage these and the super ratio of nuclear effects in tritium and helium-3 to get the F2N over F2P ratio. So this is the preliminary results, but they're not really very preliminary. Again, the publication preparation is underway, like the Hall C experiment. You will see these data coming out quite soon. You've probably already seen some of what I'm showing you in conferences and things. The super ratio that's used, it is an average of 4 different theory calculations, and the idea there was to take the standard deviation of that and use that as the model uncertainty. The real key question is if there are isoscalar effects in the neutron that are different from the proton. So different theories, different approaches. This is how the group chose to address that. Other than that, it also includes the random, systematic, and overall scale uncertainties. So the data looks like it's going to be quite nice, and it's compared to, this is some of the 6-JeV bonus experiment. The 12-JeV bonus experiment, of course, will come out here as well, and we'll look forward to that soon. Bonus, I should have said, I think it was on my slide, is just now starting to run, so we won't really have this preliminary data phase for that for a couple years, I guess, year and a half or something. And then just in my last few minutes, I wanted to point out that everything I said about D over U being very important in the valence regime for unpolarized PDFs is completely true for polarized PDFs as well. And so this is the chart that I showed you with F2N over F2P and D over U, but I could extend this on out to A1N and A1P and delta D over D. And the interesting thing, and the reason I think that this is important to point out in this talk, even though it's an unpolarized talk generally, is that these same models that predict these unpolarized numbers pick these polarized numbers. And so this is another handle on us for getting at what is that fundamental nucleon structure in the valence regime. So JLab has been dominant, I would say, in making these spin structure measurements. This is, I believe, all the world's spin structure measurements so far, and the yellow ones are all JLab, so half or more, with a focus on high precision, large X data. So this continues into the 12-JeV era. We finished A1N and Hall C just this year, and we're poised now to run D2N, which utilizes essentially the same setup. To do these measurements, we have this polarized helium-3 target. You can see here the target cell going along here up to the oven and the lasers up here installed in Hall C. We were able to achieve the highest, the luminosity which we set out to do, which is double the previous highest luminosity. Very nice. The target polarization in beam was about 55%, and it dealt with a 25 to 30 microamp beam. So this was a highly successful run, analysis underway. It's one component of a much broader JLab spin structure function program where we can combine, for instance, the neutron from Hall C and the proton from Hall B and really get a look at what is this polarized PDF picture. Once again, we need a global fitting effort to incorporate this and all the other data I showed in that chart. And so there's the Jefferson Angular Momentum collaboration setting out to do that and some others. So a broad global fitting effort aiming at valence spin PDFs, but also spin PDFs in general. So I will summarize by saying that a new generation of experiments at JLab at 12-JeV will access the regime where valence quarks dominate. The first experiments have already run and publications are coming out. So Hall C, the Precision F2 Proton and Deuteron, and Hall A Marathon. More experiments are running this year. Hall C, A1N is running, Hall B is running bonus. There are more to follow. One can get at these things, for instance, from parity violation where you can look at the D/U ratio but just in a hydrogen target, so completely without deuteron nuclear corrections. A1P, I showed you more studies. Dedicated theory efforts are also underway. I talked a little bit about CJ, a little bit about JAM. From other laboratories, there's also information. For instance, the Sequest will give us some new news about the high XC, or at least medium to high X, depending on what you call high. And I mentioned that the new WA symmetry data from Rick, we're beginning to incorporate that also into CJ. So I think as a community, it's really a great time for this science. We can expect large improvements in our understanding of the valence regime in the very near future. So not years from now, but this year and over the next year or two. I think we'll be reducing those uncertainties and beginning to reducing the uncertainties on the PDFs. That's one thing, very important, and that also helps our high energy physics colleagues, but also really getting at that fundamental nucleon structure. Which of these variety of predictions do we have? Does the nucleon really look like? So thanks. That's it.
Thank you very much, Thea, for this very nice talk. Lots of exciting new results. So if there are any questions, please either raise your hand or use the Q&A section on the app. I don't see any questions right now. So with this, we come to the end of the session. Thank you again, Thea, and
sure.
Also the end of the meeting. So don't forget about the EAC simulation Q&A session right after this. So I'm going now to hand it over to Kent, who will officially close our annual meeting. Kent?
Thanks, Carlos. I just want to thank the set of speakers we had over the past 3 days. It's really quite a set of talks, and I enjoyed them quite a lot. We went through a lot of steps getting to this meeting because we started planning for a full in-person meeting early this year, and of course things changed a lot. And it was for a while just going to be a remote sort of business meeting so that we could take care of some of the lab updates. And then some ideas for this virtual poster session, which I think evolved into some really fun event that was helped a lot by modeling on, for example, the poster session that Julie described at Ohio University. We found that there was just too much going on at JLab that needed to be talked about. So without intending a specific theme, we found that it was just hard to spend a few days together without talking about all the interesting physics that has come out and is about to come out here. The essential link for everything that's done, running the web page and putting us in touch with all the technology. I know this Blue Jeans events was difficult at times to use, but it was super important to be able to have the large number of participants that we had for this remote meeting. And she made it all work. So she's simply incredible, and I hope everybody is applauding her. Always remember, whatever your frustrations are, that Lorelei is someone who can point you in the right direction. So with that, I'd like to close it out. Thanks to all the speakers, and thanks to everybody who helped put this together.